Okay, well, let's get started then, I guess. Where do we start? Well, I guess we could start at the beginning. So, what would the beginning be? Well, let's talk a little bit about chemistry. What is chemistry anyway? When someone says the word chemistry, what pops into your head? Now is the time where a lot of people will pull out Webster's dictionary and read you a definition, but we're not going to do that. This is kind of a nice working definition of what chemistry is. It's probably not the best definition in the world or the be-all end-all, but it will get us started, right? So chemistry is the study of matter and the changes it undergoes. And we're going to kind of expound on that statement over the next 16 weeks. You'll notice in that statement, though, there's two things. There's matter and there's changes. And that's really what Chapter 1 is all about. Half the chapter is about matter, and the other half is about changes. And so that's what we're going to talk about here in this chapter. So we'll start with the matter thing first. So I guess the next question would be, what is matter? Let's see, we start at the very beginning here. We ramp up, but that's where we start. So what exactly is matter anyway? Well, matter is anything that has mass and takes up space. Everything in the universe is composed of either matter or its energy. So let's talk a little bit about matter real quick. There are three main states of matter. There's a fourth called plasma, which is a free floating soup of particles at very high temperatures, but that's not something we encounter on Earth very often. So we're going to talk about the big three here. You have solids, you have liquids, and you have gases. Okay. Solids, an example of a solid at room temperature would be like iron at 20 degrees Celsius. It's a solid. Solids have a definite shape and they have a definite volume. That's what makes a solid a solid. In other words, I could take a pencil and I could put it in a cup. The pencil maintains the shape of a pencil. I could take it and I could put it in a beaker and it's still going to be the shape of a pencil. It has a shape, doesn't matter what container you put it in. That pencil takes up a certain volume, and it doesn't matter what container you put it in. It's still going to take up the same volume. That's what makes a solid a solid. If I heat up a solid, I can change it into a liquid. And so liquids, their characteristic is they have an indefinite shape but a definite volume. Okay, an example of a liquid at room temperature would be, well, water, a cup of water. So here's my little cup of water. Here, water has an indefinite shape. I've got my water in this little cup. What shape is it taking up? Well, it's taking up the shape of the cup, all right? Well, if I take that water and I pour it into a different container, maybe I've got myself a mug here. Got visual aids today. What shape does it take up? Well, it takes up the shape of the mug. See, I could pour this into an Erlenmeyer flask. It'd take up the shape of the flask. That's what we mean by indefinite shape. Now, although it has an indefinite shape, liquids have a definite volume. If I took 100 milliliters of this water and put it in a beaker and then poured it into a flask, it's still going to be 100 milliliters. It's still going to take up the same volume, but it's going to have an indefinite shape. It's going to change shape. If I heat liquids up, I can turn them into gases. And gases have an indefinite shape and an indefinite volume. In other words, they take up the shape of the container they're in. They also take up the volume. I could have helium in a tank. It takes up the shape and the volume of the tank. I can put that in a kid's balloon, and what's it going to do? Well, it's going to take up the shape and also the volume of the balloon. I can close the door to this office, and I can pop that balloon in here. What's going to happen? Well, that helium's going to expand until it takes up the shape of the room and also the volume of the room as well. Gases have an indefinite shape and an indefinite volume. And so helium, oxygen, nitrogen, all of those are gases at room temperature. So that's the main difference between the three. Now, why do solids have a definite shape and a definite volume? Why do gases have an indefinite shape and an indefinite volume and liquids somewhere in between? Well, there's a reason why. And eventually we'll get to a point, probably at the end of this course, and I'll give you a conceptual model of what they all look like. And we'll try to explain why they have the properties they have. But for now, if you can remember that, I think that's going to be just fine. Make sense? Okay, well, let's talk a little bit about substances then. So what is a substance? Well, A substance is a type of matter that has a defined fixed composition. Okay? Substances have different properties. Okay? And it turns out that the properties of those substances can be divided into two different types. You have what we call physical properties, and you have what we call chemical properties. Physical properties are properties which can be measured without changing a substance into another substance. In other words, the only type of change you have is what we call a physical change. I don't create anything new. All right. Chemical properties are properties which show themselves by changing the substance into one or more different substances. In other words, what we call a chemical change. One way you can look at it is physical properties tell what a substance is, and chemical properties tell what a substance does. Make sense? All right, well, let's see if it does. All right. Anytime you see the words reacts with acid, reacts with water, reacts with oxygen, reacts with carbon dioxide, reacts with iodine, anytime you see those words, red flag, that's a chemical property because it's reacting with something. All right. How about color? Well, color is a physical property because I can measure that without changing it into something else. This is a lot more fun when the notes are actually already filled in. For example, I can take a beaker of salt, I can look at it, and it's white. Well, did I change that salt by looking at it? No, I just looked at it, it's white. So that makes it a physical property. How about melting point, chemical or physical? Well, that's a physical property. You might say, but I took ice and I melted it, and now it's water, I've changed the substance. Have I really changed the substance? Well, no. All I've done is I've taken H2O, water, and I've changed it from its solid form here into its liquid form here. All right, and so I've changed the state of it, but I haven't really changed it into a new substance. So melting point is actually a physical property. Boiling point would be the same. All right, flammability. What does flammability mean? Well, flammability means does it burn? Okay, some things burn, some things don't. Is that a physical property or is that a chemical property? Well, that's a chemical property because when something is burning, what's it doing? Well, it's reacting with oxygen. See, this is rapid oxidation. This is why you can smother out a fire. If you put a blanket over a fire, it goes away because, well, there's no more oxygen there, and so your stuff stops burning. So, yeah, that's definitely a chemical property. All right, what about mass? Well, it's a physical property. I can take a block of lead and put it on the scale. Weighs 200 grams. Did I change that lead in any way by putting it on the scale? No. So therefore, physical property. All right. Rusting. Some metals rust, some metals don't. Is that a physical property or a chemical property? Well, it's a chemical property. When something is rusting, what's it reacting with? What's reacting with oxygen? When something is burning, what's it reacting with? Well, it's reacting with oxygen. So actually, chemically, rusting and burning are actually the same process. The only difference is a matter of speed. Burning is rapid oxidation. Rusting is slow oxidation. So if I have a barbed wire fence and it's sitting out there on the prairie, you mean it's actually giving off heat as it's rusting? Yeah, actually it is. But it's giving off that heat so slowly that it's bleeding into the atmosphere, it's imperceptible, you can't tell. But yeah, actually it is giving off heat. It's just giving off very slowly. So chemically, those are actually the same things. Okay? But they are chemical properties because a chemical change, you're changing a substance into something different there. Make sense? If I gave you a property, could you classify as chemical or physical on a test? All right. Well, that's one way that you can divide the properties up. So what's another way? Well, a second way that you can divide properties up are intensive versus extensive properties. Okay, an extensive property, those are properties that depend on the amount being measured. So let's say, for example, mass. If I have a little bit of sugar and I have a lot of sugar, are they going to weigh the same or are they weigh different? Well, I mean, the big packet of sugar is probably going to weigh a lot more than the little packet. It depends on how much you've got. So mass is an extensive property. What about volume? Well, volume is also an extensive property. because it depends on how much you have. A big beaker of hydrochloric acid is going to take up more volume than a little beaker. So those are extensive properties. Intensive properties are properties that don't depend on the amount of substance being measured. For example, density. Lead, if I have a lot of lead, it probably weighs more than a small amount of lead, but they both have the same density, mass over volume, grams per milliliter. Color, a small beaker of salt is the same color as a large beaker of salt. So that's an intensive property. Hardness, small diamond, big diamond. Melting point, boiling point. Water boils at 212 Fahrenheit or 100 degrees Celsius. Doesn't matter if it's a lot of water or a little water. That's an intensive property. If I gave you a property, could you classify it as intensive or extensive? Okay. Now, why is this important? Well, this is kind of important because, every once in a while someone brings you, a packet of white powder and says, what is this stuff? Well, there's a lot of stuff out there that's a white powder. It could be sugar, could be flour, might be salt, might be cocaine, Who knows? There's a lot of things out there white powder. Well, the nifty thing is, there are people willing to pay you a lot of money to figure out what that white powder is. All right, so yeah, you could actually make some money off this. So the question is, how do I tell? How do I figure out what this stuff is? Well, one way that you can figure out what a substance is you can measure its properties, because every single substance has its own distinct set of properties. Now, you have a lot of things out there are white powders, but maybe, there are very few things that are a white powder that have a melting point of 125 degrees Celsius, and have a density of 2.67 grams per milliliter. So if you can measure enough properties, what you can do is you can start narrowing things down, and you can actually figure out exactly what that substance happens to be. Make sense? Okay, so let's say, for example, you got your little vial of white powder there. So here's kind of the question. Do you think extensive or intensive properties would be more useful here? Well, probably intensive, right? I have 30 grams of a substance. What is that substance? Well, I don't know. It could be anything. I can have 30 grams of lead or tungsten or iron or water. So an extensive property is not going to help me. Okay. So intensive properties help me to identify things. Which would you want to measure first? Physical intensive properties or chemical intensive properties? Well, I would rather measure the physical intensive properties first. For example, let's say, I've got a liquid and I've got a small vial of it, and I want to see if it's flammable. So I take a match and I light it up, and hey, it turns out it's flammable. It burns up. What am I going to do now? Well, I'm not going to do anything now, because the problem is I've used it all up. I burned it up, right? Okay, well, let's take that same vial, and maybe I measure the density of that liquid. I take the mass and divide it by its volume. Or I look at refractive index, or I measure something like that. Have I changed the substance into anything else? Well, no, I still have my sample. So normally what we try to do in the case, especially when you have very little of something, is we measure physical intensive properties first, and then we do the chemical, because you can measure the physical properties without destroying your sample. Now, if you've got a lot of it and it doesn't really matter, I guess you can do whatever test you want to do, or if it's really cheap. But if you have a very little amount of it, then you might want to do the physical tests first, because if you do the chemical tests, you normally change it into a different substance and you're out of sample. Now, I'm not saying chemical property tests aren't important. Sometimes there's a particular chemical property test and it just really nails down what the identity of your unknown is. All I'm saying is it's usually more useful to do the physical property tests first and then do the chemical property test. And so, yeah, this is very important to a chemist, because sometimes we get in the lab and we have to identify things. What is this stuff? That's the fun part of the job, actually. It's kind of like a little puzzle. Okay, so if I gave you a property, could you classify it as physical or chemical? Could you classify it as extensive or intensive? Well, those are properties of substances. Let's talk about types of substances. Turns out that you can divide all substances into three different types. The first type of substance you run into are what we call elements. Elements are the basic building blocks of matter. So let's say, for example, back when you were 8 years old, you had Lego blocks. Remember Lego blocks? Big giant bag of Lego blocks, and you could just build all sorts of things. And you had blue Lego blocks with 3 pegs, and you had red Lego blocks that were kind of like a square and had 4. You had long, skinny black Lego blocks. And you took all those things and you built all sorts of stuff like forts and Death Stars and cars and such things. If you were kind of like me, kind of unimaginative, you built a big giant tower, just a big giant brick. That's about all I could do. All right, and then what you did when you got done is you kind of tore them back apart, put them back in the bag, and so that's the fun part, was tearing it apart. And then you left 1 or 2 on the floor so your dad would step on them, with their bare feet in the middle of the night. And that was it was fun being a kid, wasn't it? Right? Well, elements are kind of the same way. Elements are your Lego blocks of the universe. Okay, it turns out that there are 90 naturally occurring different Lego blocks, for lack of a better phrase, in the universe, and these are what we call elements. And everything in the universe is made up of these elements. Sometimes you find the elements apart, sometimes you find them snapped together, but everything is made up of these elements. All right? Once you take let's say for example you built yourself a big giant tower and you tore it down. Once you get down to a red Lego block that has 3 pegs, you can't tear that in half again unless you're an exceptionally strong child. You're down to the fundamental unit, right? Well, that's the way it works with elements. Once you get down into an element, you cannot break those down into simpler substances by ordinary means. All right, some examples of the elements that we find are found in the periodic table. And the periodic table is a listing of all the elements, and they're arranged in a certain way. Quite a bit of this course is devoted to figuring out how the elements in the periodic table are arranged. You can learn a lot if you know what to look for from that. All right, and we'll talk about that as we go through the semester. Chemists are basically lazy by nature. I mean, we could write the names for everything down, but that's a lot of writing. So what we have created is we created symbols for the elements. And symbols for the elements are either 1-letter or 2-letter abbreviations that specify which element we're talking about. When you write symbols for elements, it's always big letter, little letter, if you have a 2-letter symbol, always. You're not allowed any leeway there. You're not allowed artistic interpretation. This is not art. This is science. It's always big letter, little letter. Okay, so don't try to get all hip on me and write 2 little letters or 2 big letters, because that's not the way it works. All right, so for example, if I'm talking about nitrogen, what do you think would be a great abbreviation for nitrogen? Well, how about N? That works really well for me. So that's the abbreviation for nitrogen in the periodic table. Carbon, what would you do there? Well, I'd probably do C. That works for me. So C is carbon. How about sulfur? Well, S. See, this is an easy course. Chemistry's easy. All right. What about silicon? Well, S is already taken, so I can't do S. So for silicon, the symbol is Si. Okay. Sometimes the abbreviations are the first 2 letters in the name. They don't have to be. Sometimes it's just 2 letters in the name. For example, zinc. Abbreviation for zinc is Zn. All right. But generally, most of them tend to make sense. If you look at the abbreviation, you look at the name, it's like, okay, I see how they came up with that. Do you have to memorize every single element and every single symbol in the periodic table? No, you don't have to do that. You're probably never going to run into erbium, and so you probably don't have to know that one. Are you ever going to run into chlorine? Yeah, you're going to see a lot of chlorine, so you probably need to know the symbol for chlorine is Cl. Probably somewhere along the way, someone back in high school made you memorize the elements and the symbols in the periodic table. They did that because, to be honest, you didn't know enough math to be able to do anything interesting yet. So you memorize symbols for elements, and you balanced equation after equation after equation. And that's what they did to you. Both of those are skills that, are kind of useful, but I'm not going to make you memorize every element in the periodic table. just know the common ones. And there's probably a list somewhere in your book of common elements and symbols in the periodic table. You will get to know them as you use them. It's like anything else, like any other foreign language. You probably don't learn Spanish unless you actually, have to find the bathroom somewhere in Mexico City. You learn Spanish really quick by doing that. How about lead? Well, lead is Pb. Pb, I don't see a P or a B in lead. Well, here's where it gets a little tricky. Some of the elements have symbols that are based off their Latin names. Back in the 1700s, 1800s, people took Latin, and they spoke Latin, and they wrote entire treatises in Latin. And it was a way to show off. It was a way to show off how much more educated, you were than this other person who didn't speak Latin. Today, there's a lot of Latin in science. In fact, if you're talking about genus and species, and you'll see all sorts of Latin names in biology. In fact, the words genus and species and phylum, those are actually Latin terms as well. So it can be useful to know Latin terms, although no one speaks it, because it does pop up in science. The Latin word for lead is actually plumbum, and that's where the Pb came from. What word does that sound like that we use today? Well, plumbing, plumber. What did pipes used to be made out of? They used to be made out of lead. That's actually where it came from. All right. How about silver? Well, that's Ag. That stands for argentum, and that's the Latin name for that. Sodium. Well, that's Na. That's natrium. Iron. Well, iron is Fe. That's ferrium. Potassium. That's actually K. That's calcium. What's the symbol for tungsten? Tungsten is actually W. That's wolfram. And that's where the symbol actually came from. Where do you find tungsten? Well, tungsten's found in filaments, in light bulbs, the regular incandescent type, not the ones that they have these days. Very high resistance of electricity, which is kind of odd for a metal. So you put electricity through the filament, and it puts up a resistance, and that resistance dissipates that energy in the form of a lot of heat and also a lot of light. And that's how light bulbs work. You also see it used in, for example, rings. This is tungsten carbide, which is a very hard substance. Yeah, that's what my wedding ring is. My wife bought me a gold one, and sometimes she gets annoyed I don't wear it. But, it's amazing what you can find on eBay for $25 if you're willing to wait for something to come from Hong Kong for, 2 or 3 weeks. I don't mean to imply that most of the elements have these really weird symbols. They don't. Most of them make perfect sense. Cobalt, for example, is CO. Makes sense. But there are a few that don't. And so if you see a symbol that doesn't seem to make sense, it probably comes from that Latin name, and that's probably what's going on. Okay? Know the ones for the common ones, and I think you're probably going to be okay. All right, well, if it's an element, it's in the periodic table. That's a really easy way to tell. If you look at the periodic table, it's sitting there, you know it's an element. All right? Compounds contain 2 or more elements with fixed mass percents. All right? In other words, compounds are kind of like my Lego blocks when I snap a couple of them together. In a compound, you have 2 or more elements, and they're bonded together. They're kind of like the things that you actually build with your Lego blocks there. Okay? They always have fixed mass percents. Compounds also have different properties from the elements from which they were made. So, for example, let's talk about sodium chloride. Sodium chloride, of course, is the chemical name for what? Well, it's just salt, common table salt. If I took table salt, I can break that down. It's NaCl. I can break that down back into its 2 individual elements, because I can break a compound down into its elements. Now, it takes chemical means to do it, but it is possible. So electrolysis would probably be the way to go here, the easiest way to do both of these. Run electricity through it, and I can break that down into sodium and chlorine. Well, here's the deal. It doesn't matter where I get the salt from. When I break down 100 grams of salt, I always get 39.34 grams of sodium and 60.66 grams of chlorine, because those are the mass percents. And it doesn't matter if I get it from the Pacific Ocean, or if I get it from a salt mine in Louisiana, or if I go to the grocery store and buy it, as long as it's pure salt. It's got to be pure salt. But as long as it's pure sodium chloride, you always get those percentages every single time. And that's what we mean by fixed mass percents. Okay, water. If I break water down into its individual elements, which would be hydrogen and oxygen, 100 grams of water always gives me 11.19 grams of hydrogen and 88.81 grams of oxygen. Always. If it comes from the Nile River or it comes from your faucet, if it's pure water, always get those percentages, fixed mass percents. Why do I always get those fixed mass percents? Well, we're going to talk about it. So, by the way, I'm going to do that to you a lot. We'll talk about something, I'll say, yeah, we'll talk about that later. And we will. And sometimes it may be, 6 weeks down the road, and I'll say, hey, remember when we said we'd talk about this? So sometimes you have to be a little patient, but keep in mind that what I'm doing is I'm kind of drawing you a picture. When you draw a picture of a horse, you don't draw the eye first and fill it in, and then draw the nose. You sketch the outline first, and then you come back in and fill in things. So that's kind of what we're doing here. So it might be a little frustrating at first when I keep saying, yeah, we'll talk about that. But you just got to be patient. Now, if you're patient and you hang around long enough, I will get back to it. It just we got to sketch the outline first. By the way, autistic people will actually draw the eye first. They will draw the part instead of the whole. Interesting fact, I guess. It's not on the test, but I thought it was interesting. But yeah, that's not what we're doing. So yeah, I'll get back to it. Just hang in there. Okay? All right. Well, compounds. What do you know about sodium? Sodium metal. Well, sodium metal is kind of a grayish, silvery metal. They ship it to you, and it's actually packed in mineral oil. All right? And the reason why is sodium metal is extremely reactive with water. If you take a piece of sodium metal and you throw it in a beaker of water, if it's light enough, what it will do is it'll actually whiz around on top of the water. Okay? If your ventilation is restricted enough, the next thing that will happen is it'll catch on fire. So you get this little thing on this whizzing around on top of the water, and it's actually on fire. If your ventilation is restricted enough still, the next thing that happens is it actually explodes. And so this is why I don't normally do that when it's a classroom demonstration, because yeah, you can blow up a glass beaker, and it's not cool to shower your students with flying glass particles. So yeah, I don't usually do this in the classroom. But yeah, that's what actually happens. It's very reactive. Think you'd ever want to eat a piece of sodium? That would be an extremely bad idea. In fact, you don't even want to touch it, because what it will do is it will actually combine with the water from your hands, the sweat in your hands, and it will form concentrated sodium hydroxide, which is a very strong base, which will actually burn your hands very badly. So you get these really bad base burns from this stuff. So I don't even want to touch this stuff, much less eat it. Very nasty stuff. Okay, what do you know about chlorine gas? Well, chlorine gas is kind of a pale yellowish gas, and it's actually one of the first weapons of mass destruction. Back in World War I, what they did is they actually used it as they hid it out in the fields. This is back when they were doing trench warfare. You dig a trench and you sit in the trench and you shoot at people on the other side in the other trench. And then after a while you get tired of being in the trench, so you charge and you take some ground and you dig another trench. And then you just keep doing this over and over. Well, the Germans actually put some of these chlorine gas canisters out there in the field. And when the Allies came running by, they released them. Chlorine gas gets in your eyes, it gets in your throat, and it forms concentrated hydrochloric acid. And if you've ever got a whiff of it before, I have actually. I had a student when I was in school, a fellow student, generate some chlorine gas and was pointing his test tube toward another student, which you never do, by the way, when you're heating up a test tube. Watch the safety video and you'll see that. And what happened was this chlorine gas was evolved from this particular reaction, And you know, that kid, he got as red as this shirt and started coughing. And I was on the other side of the table, and I got a whiff of it, and it kind of just, it's almost like someone just reached down the back of your throat and just grabbed your breath and pulled it away from you. Your airway just spasms. You know, if you get enough of it in there, it'll get in your lungs and form concentrated hydrochloric acid, which is really bad for your lungs. It will get in the water in your eyes, and yeah, it's like having acid in your eyes. You'll go blind. And so, you know, 3,000 people got a whiff of this stuff, and they didn't know what was going on, and they started going blind, and it was just all sorts of panic going on, and it was bad. And that's actually how, that was the first weapon of mass destruction. And so, you know, they developed things, of course, you know, how humans are, even worse than that, like mustard gas and sarin and stuff like that. And eventually they just banned them, said, this is way too much for war, even war. And so, yeah, you don't see chemical weapons used in war anymore, at least, you know, out in the open. But yeah, there's still stockpiles of stuff. But that's chlorine. So yeah, you certainly don't want a whiff of that. So I got this sodium over here, which is just horrible. You know, I don't want to eat that, don't want to touch that. I got this chlorine, I certainly don't want to breathe that. So when I put those two things together, I ought to get something really bad, right? Well, what happens when I put sodium and chlorine together? I get sodium chloride, which is salt. Something completely harmless. In fact, something you need in your diet every day, a certain amount of salt. All right. So moral of the story is compounds have different properties from the elements from which they're made. Just because you have two things that are really, really bad and you put them together doesn't mean you're going to get something together that's bad. It might be harmless. Now, sometimes you can take something that's bad and put it with something else that's bad, and you get something that's 5 times worse. Doesn't mean it's going to be harmless either. But compounds have different properties from the elements from which they're made, and that's the key. Okay, well, together, your elements and compounds make up what we call your pure substances. I can have pure water. I can have pure nitrogen. I can have pure sulfur. All right. So everything else would be classified as an impure substance. And those impure substances are what we call mixtures. Okay. And it turns out you can divide those into 2 more categories. So I guess there's really kind of 4 things here that we're talking about. All right. But I see that we've kind of reached the 30-minute limit there. So I'll tell you what we're going to do. I'm going to go ahead and stop it right here. And we'll talk about mixtures in the next video. So that's 1 down. So we'll go from there. We'll finish up chapter 1 here in 1 or 2 videos, depends, I guess. And we'll move on from there. So until next time, we'll see you in the second video. Bye.